Introduction. The Energy Policy Act of 1992 requires what federally owned vehicle fleets include alternative fuel vehicles. The 1992 Energy Policy Act requirement can be met with flex fuel vehicles capable of using conventional gasoline or an 85%/15% blend by volume of ethanol and gasoline known as superethanol. Currently, the United States is the largest producer of the ethanol fuel and utilization of domestically produced energy reduces U.S. reliance on imported petroleum. Key air pollutants of concern associated with light-duty vehicles include carbon dioxide, carbon monoxide, nitrogen oxides, and hydrocarbons. Carbon dioxide is a key greenhouse gas. Carbon monoxide, nitric oxides, and hydrocarbon have various adverse effects on human health, including increased morbidity and premature mortality. For example, carbon monoxide causes adverse effects to the central nervous system. Oxides of nitrogen cause adverse effects to the lower respiratory system. Hydrocarbon includes a large number of chemical species that pose a range of adverse health effects, ranging from toxicity to cancer. In 2009, SHI compared fuel consumption and tailpipe emissions from one flex-fuel vehicle Ford Focus operated on superethanol and gasoline based on real-world activity data. However, few studies have quantified the real-world emissions of flex-fuel vehicles operating on superethanol compared to similar gasoline-fueled vehicles. The main objectives of this research are to quantify the theoretical expected difference in fuel use and carbon dioxide emission rates for superethanol versus gasoline, quantify the trends in fuel use and emission rates versus engine load for similar vehicles fueled with superethanol and gasoline, and compare and discuss the percentage difference in cycle average fuel use and emission rates between superethanol and gasoline. Methodology. The methodology section provides a brief overview of the basis for developing a theoretical expectation of differences in fuel use and carbon dioxide emission rates for superethanol versus gasoline, and of the study design for real-world data collection of selected vehicles. Theoretical expected difference in fuel use and carbon dioxide emissions. The theoretical calculation of fuel consumption and carbon dioxide emission can be used to compare expected theoretical and measured real-world difference. For the same heating value content, the difference in the mass of fuel required for superethanol versus gasoline is estimated based on fuel heating value. Similarly, the difference in the amount of carbon dioxide emitted for the same amount of heating value is estimated based on the heating value, density, and weight % of carbon for each fuel. The primary assumption is that the vehicle consumes the same amount of energy regardless of the fuel. The key physical and chemical properties of superethanol and gasoline are given in Table 1. Study design, second-by-second fuel consumption, and emission rates of a 2008 flex-fuel vehicle Dodge Avenger operated on superethanol and a 2012 flex-fuel vehicle Dodge Avenger operated on gasoline fuel were measured using a portable emission measurement system. Tailpipe exhaust carbon monoxide, carbon dioxide, nitric oxide and hydrocarbon concentrations were recorded at 1H ED using the portable emission measurement system. The 2008 Dodge Avenger has a 2.7-litre 6-cylinder 189 horsepower engine. The vehicle has a gross weight of 4,497 pounds and was measured during 112.9 miles of on-road driving in Havelock, North Carolina. The 2012 Dodge Avenger has a 2.4-litre 4-cylinder 173 horsepower engine. The 2012 vehicle has a gross weight of 4,600 pounds and was measured during 112.0 miles of driving in Raleigh, North Carolina. Real-world vehicle activity data was measured using an onboard diagnostic scan tool and multiple global positioning system receivers with barometric altimeters. Vehicle-specific power, which is a function of vehicle speed, road grade and acceleration, is a useful indicator of engine load. Vehicle-specific power was calculated based on the second-by-second vehicle speed, road grade and acceleration data 6 and was categorized into 14 modes defined by Frey in 2002. Modal average, energy consumption and emission rates, with 95% confidence intervals, were estimated and compared for the gasoline and superethanol-fueled vehicles based on the observed data set for each vehicle. The driving in both Havelock and Raleigh included arterial and freeway routes. For the purpose of estimating cycle average emission rates based on real-world driving, and to enable comparisons between the two vehicles for the same driving cycle, The modal average rates for each vehicle were weighted based on a fraction of time spent in each mode for the observed driving cycle in Raleigh, given in Table 2. Results and discussion. Fuel consumption and tailpipe emissions for both superethanol-fueled and gasoline-fueled vehicle are quantified and compared based upon expected theoretical values and real-world measurements. Theoretical comparison. For the same energy input, the mass of fuel consumed for superethanol is nearly 49% greater than for gasoline, as shown in Table 3. Similarly, the volume of superethanol consumed is nearly 40% greater than for gasoline. Because superethanol has lower carbon content, the tailpipe carbon dioxide emissions are expected to be 1.8% lower than for gasoline. Furthermore, the volume-based superethanol carbon dioxide emission is estimated to be nearly 7.4% lower than for gasoline. However, unlike gasoline, a portion of the carbon dioxide emissions from superethanol are based on biogenic sources of carbon, and thus do not make a net contribution to atmospheric carbon loading. Measurements. For the 2008 Dodge Avenger, 10th to 43 seconds of valid and age-said data were obtained from 112.9 miles of driving in the Hayvok area. The proportion of valid to raw data was 99.3%. For the 2012 Dodge Avenger, 10th and 70 to 76 seconds of valid and age-said data were obtained from 112.0 miles of driving in the Raleigh area. The proportion of valid to raw data was 99.9%. The results for vehicle-specific power modal average fuel use and emission rates for both vehicles are given in Figure 1. Vehicle-specific power modes 1 and 2 are for negative values of vehicle-specific power, representing deceleration or driving down a hill. There is no load on the engine for vehicle-specific power modes 1 and 2, and thus the fuel use and emission rates for these modes are generally relatively low. Vehicle-specific power mode 3 includes idling, for which there is no load on the engine. Vehicle-specific power modes 4 to 14 are for ranges of increasing positive vehicle-specific power, which can represent acceleration, steady speed cruising, climbing a hill, or combinations of these. The fuel use and emission rates tend to increase with increasing positive vehicle-specific power for both vehicles. For most modes, the mass of fuel consumption for the superethanol-fueled vehicle is higher than for the gasoline-fueled vehicle. The exception is for modes 12 to 14, for which the sample sizes of 1HZ data are relatively small compared to other modes, and thus for which the modal estimates are not as precise. Typically, over 99% of the carbon in the fuel is emitted as carbon dioxide. Therefore, there is a linear relationship between fuel use rate and carbon dioxide emission rate, and the relative trends in fuel use rate and carbon dioxide emission rate among the modes are similar. However, because superethanol has less carbon per unit of energy than gasoline, the carbon dioxide emission rate for superethanol is typically lower than for gasoline. For the gasoline-fueled vehicle, the modal average nitric oxide emission rates are highly sensitive to engine load for very high engine load, as indicated in Figure 1 for modes 12 to 14. However, the nitric oxide exhaust concentration for the superethanol-fueled vehicle was generally low throughout the range of engine loads. There is some evidence, however, that the gasoline-fueled vehicle operated differently than the superethanol-fueled vehicle at high engine load, as indicated also by the relatively high carbon monoxide emission rates for the gasoline vehicle in modes 12 to 14. The hydrocarbon modal average emission rates were higher for the superethanol-fueled vehicle for all modes. The relative difference in fuel use and emission rates is quantified for modes 1 to 11. Modes 12 to 14 were excluded here because they had relatively small sample sizes. The differences in modal average fuel use mass rates for the superethanol-fueled vehicle versus the gasoline-fueled vehicle range from plus 17% to plus 140% among these 11 modes. The percentage difference tends to decrease with increasing vehicle-specific power. The differences in modal average carbon dioxide mass emission rates range from 23% to plus 60% among the first 11 modes. For nitric oxides, the modal average rates for the superethanol vehicle are 95% to minus 87% lower than for the gasoline vehicle. The superethanol-fueled vehicle had 33% to 74% larger modal average carbon monoxide emission rates. However, the superethanol vehicle has 110% to 270% higher modal average hydrocarbon emission rates. there can be substantial variability in emissions of nitric oxides, carbon monoxide, and hydrocarbon when comparing vehicles of similar manufacturer and Model 8, and thus the comparison of nitric oxides, carbon monoxide, and hydrocarbon here between one superethanol vehicle and one gasoline vehicle cannot be extrapolated to an overall conclusion regarding differences between the two fuels. Therefore, the comparison should be extended to include more vehicles. The difference in fuel use and emission rates for the two vehicles are compared based on the observed Rayleigh driving cycle. The cycle average fuel use mass emission rate is 1.08 and 1.45 g/s for the measured gasoline and superethanol vehicle, respectively. Therefore, the cycle average fuel use mass emission rate is 34% higher for the superethanol vehicle than for the gasoline vehicle. While the difference is not as large as the theoretical expectation of 49% difference, it is nonetheless a substantial difference. The volume-based cycle average percentage difference of superethanol fuel consumption versus gasoline is 27%, which is smaller than 40% difference based on the theory. Since the vehicles are not identical, there could be inter-vehicle variation that affects the comparison. The smaller than expected difference may indicate that the E85 fueled vehicle is more energy efficient than the other. In 2009, Shai reported 31% and 38% volume-based percentage differences in superethanol versus gasoline fuel use for Ford Taurus and Chevrolet Lumina vehicles, respectively. The cycle average carbon dioxide emission rate is 3.40 and 3.02 g/s for the gasoline and superethanol vehicle, respectively. As expected, the cycle average carbon dioxide mass emission rate for the superethanol vehicle is lower than for the gasoline vehicle. However, the difference of -11% is larger in magnitude than expected and indicates that the superethanol vehicle may have better energy economy than the gasoline vehicle. The cycle average nitric oxides emission rate is 0.95 and 0.07 g/s for the gasoline and E85 fueled vehicle, respectively. Similarly, the cycle average hydrocarbon emission rate is 0.17 for the gasoline vehicle and 0.43 g/s for the superethanol fueled vehicle. The cycle average carbon monoxide emission rate is 8.55 and 5.45 g/s for the superethanol and gasoline vehicle, respectively. The cycle average nitric oxides emission rate for the measured superethanol vehicle is 93% less than for the measured gasoline vehicle, whereas average carbon monoxide and hydrocarbon rates are 57% and 150% higher, respectively. Summary: this study is a preliminary demonstration of a methodological approach for measuring and comparing superethanol versus gasoline-fueled vehicles based on real-world data. Theoretical percentage differences in fuel use and carbon dioxide emission rates were estimated based on fuel properties of superethanol and gasoline. The differences in fuel use and carbon dioxide emission rates for the superethanol versus gasoline-fueled vehicle were qualitatively consistent with theoretical expectations, but differed quantitatively. Observed differences in nitric oxide, carbon monoxide, and hydrocarbon emission rates between the two vehicles cannot be extrapolated. However, the results here illustrate that although a superethanol-fueled vehicle may typically have a lower carbon dioxide emission rate than a gasoline-fueled vehicle, the emission rates of other pollutants, such as carbon monoxide and hydrocarbon, can be higher. Larger samples of both superethanol and gasoline vehicles are needed to develop a robust quantitative comparison. Acknowledgement: this material is based upon work supported by the National Science Foundation under Grant No. 0756263. Any opinions, findings, and conclusions or recommendations expressed in this material are those of the authors and do not necessarily reflect the views of the National Science Foundation.